it's a paper about certifying rings of integers in number field. And yeah, perfect. So Alain is connected. Hello?
Hello.
Can you hear us? Yeah. Perfect. We can hear you, but we still can't see your slides.
Yeah.
I guess they will appear at some point. Maybe not.
It was working a few minutes ago.
We just need to wait a bit and it will show up, hopefully.
You see?
Yes. Anna, maybe you can put your mic a bit up. We can't hear you very well.
Yeah. Oh. You still can't hear me?
Internet. Maybe your network connection is not that good.
Yeah, so I was having trouble with that, but then I moved. I tried a different network.
Maybe if you could try restarting
and it was
the app,
yeah,
that might fix the internet issues.
Yeah. Okay, you can see it now? Can you?
Okay, it's working now. We can see your slides. Yeah, we still see a bit of the top bar at the top, but I guess it's okay. I mean.
Yeah, but okay. Yeah, so I'm gonna talk about joint work with Anne Baanen and Sander Dahmen about certifying rings of integers in number fields. Can you hear me okay? Sorry, can you hear me?
Yes, we can hear you, but we are trying to make your volume a bit higher.
Yeah, we're working on turning up the volume a bit, but we can hear you.
Okay. Okay, cool. So let me tell you a bit about the motivation of this problem. So many problems in number theory require explicit computations. And for example, one of these problems is solving some type of equations that we call Diophantine equations. And these are equations that we want to solve over the integers. And in order to do this, we need to compute explicit objects, such as the ring of integers of a number field or its discriminant. And I will tell you more about this a bit later. But in principle, we could use a computer algebra system to try to compute them. So for example, SageMath or Mathematica. But the problem is that even though computer algebra systems are efficient, they are not always correct. So one of the aims of this project is to be able to verify in Lean the computation of one of these objects, which is the ring of integers of number fields. And the approach that we use is a certification approach. So we're going to use a computer algebra system, in our case, SageMath, to compute a certificate and output Lean code with a proof that can be imported and checked in Lean. And we do this to formally verify some of the entries in the L functions and modular forms database. So to start with some definitions, a number field K is a finite field extension of the rational numbers Q. This means that K is itself a field that contains the rational numbers Q. And when we look at it as a vector space over Q, its degree is equal. So its dimension is finite, and we call this dimension the degree of K. So this definition was already in MATLAB as a type class. So here are some examples of number fields. The rational numbers are a number field of degree 1. The rational numbers adjoin a square root of 3. This is a number field of degree 2. But I could also consider adjoining some root theta of a cubic polynomial like this one, x cubed minus 3x plus 10, to the rational numbers. And then I obtain expressions of this form. And this is going to be a number field of degree 3. So it turns out that any number field is isomorphic to Q adjoin a root alpha of a polynomial, an irrational polynomial over the rational numbers. So over the rationals, modulo some polynomial f. Now inside these number fields, there exists a very special ring, which we call the ring of integers of k. And this is the analog of how z, the integers, live inside the rational numbers. So to be more precise about the definition, the ring of integers of a number field k is defined as the integral closure of z in k. What this means is that OK, the ring of integers of k, is going to be those elements x in k that are roots of a monic polynomial with integer coefficients. And just to recall, a monic polynomial is a polynomial that has a leading coefficient equal to 1. So this object is one of the foundational objects in algebraic number theory. And indeed, in MATLAB, this has already been defined. You can see that the ring of integers of k is just the integral closure of z in k. But this ring has a very nice property of having a z basis. So this means that there is a collection of elements, say omega 1 to omega n, such that any element in this ring can be written in a unique form as a linear combination of these omegas, where the coefficients lie in z. So some examples are the ring of integers of the rational numbers, which is just z, as you would expect. The ring of integers of the rational numbers adjoin a square root of 3, and we obtain expressions of the form a plus b times the square root of 3, where now a and b are integers. And this is, we can also write it as z adjoined the square root of 3. But it gets a bit more complicated when we consider higher degree examples. So, for example, if we adjoin a root theta of the polynomial x cubed minus 3x plus 10 to the rational numbers, and we consider the ring of integers of this number field, we get expressions of this form. So we can see in this last example that 1 theta and theta minus theta squared divided by 2 is an integral basis for this number field. But we can see that in the second example, we were able to write this ring of integers as z adjoined some other element, but it turns out that we cannot always do this. So in the case that OK cannot be written in this form, so z adjoin some gamma, then we say that this ring of integers is not monogenic. So now that I gave you the basic definitions, let me describe the setup. So we have k, a number field that we obtain by adjoining a root of an irreducible monic polynomial with integer coefficients. And we can write this in line with the predicate is adjoin root k and then map something f. And this map, some map between z and qf, what we're saying here is that we are considering this polynomial f, which lives, which has coefficients over the integers. We're just going to consider it as a polynomial over the rational numbers. So this is just saying that k can be obtained by adjoining a root of f. So suppose that we are told, perhaps by your favorite computer algebra system, that a subring O with an explicitly given z basis is a ring of integers of a number field. The main question that we want to solve is how can we formally prove that O is indeed equal to the ring of integers of k. So in Lean, this would mean that we have something of type subalgebra of k, so we should think of this just as being a subring of k. And we want to prove that this O is equal to the ring of integers of k. And we are assuming that we know O explicitly. Perhaps we know a z basis of O. So two initial questions come into mind. First, how should we define O in Lean? And second, how can we compute in it? So in order to be able to solve these questions, we first need to consider efficient polynomial arithmetic. So the way polynomials are defined in MathLib, in the Lean mathematical library, is not suitable for computation. So in fact, the polynomial arithmetic is non-computable. So we will use an alternative representation of polynomials over a ring R, and we're going to represent them as lists over R. So these lists will correspond to the coefficients of the polynomial. And we have a map that goes from lists over R to the MathLib polynomials over R. And here we have the description, polynomial.offList takes as input a list over R and outputs the corresponding polynomial in MathLib. And we also define operations on lists corresponding to addition and multiplication on polynomials. So we can translate statements about addition and multiplication of polynomials into this setting of lists. And we define computable polynomials as a subtype of those lists that have no trailing zeros. And this is similar to the way polynomials are defined in MathComp, in the MathComp library for Coq. So they also use lists for defining polynomials. And we prove, or we define the isomorphism between computable polynomials over R and the MathLib polynomials over R. So now that we can compute with polynomials, let me tell you how we can define this subring O. So again, we say that we write K is just Q adjoin some root theta of a polynomial f. And suppose we have a basis omega 1 to omega n, which is given to us as a z basis for O. So as a set, if I want to define this in Lean, I would say perhaps take the z span of this set of omega i's. But the problem is that if I do that, then this thing is going to have type a submodule of K, a Z submodule of K. But I wanted to have type a Z subalgebra of K. So we need to convince Lean that this set, the Z span of these omega i's, is actually closed under multiplication. And we can do this by writing each omega I as 1 divided by some non-zero integer d times a polynomial bi evaluated at this root. And every omega I can be written in this form. So see, if we want to prove that this set, the Z span of the omega i's, is closed under multiplication, this boils down to proving that omega I times omega j can be expressed as a linear combination of the omega k's, where the coefficients are integers. And this, in terms of polynomials, is equivalent to proving that there exists a polynomial Sij, such that this equality over polynomials holds. So in order to prove that this set is closed under multiplication, we can provide the integers aijk, the polynomials sijk, and then the proof just reduces to checking some number of polynomial identities, which we can do because we can compute with polynomials. And what we do is all this data, so these polynomials bi's, which are used to define the basis, the omega i's, the integers aijk's, and the polynomials sij, we incorporate them, we bundle them together with proofs of, for example, these polynomial identities into a structure that we call the subalgebra builder. So for example, in this number field, which we obtain by adjoining a root of this cubic polynomial, we have that this ring O given to us by a computer algebra system is the ring of integers. And we want to prove that, but first we need to construct this O. And this O is given with the Z basis 1, theta, and theta squared divided by 3. So we put this data in to construct something of type subalgebra builder. We include this data as part of the fields. So for example, you can see a field called B and this includes the polynomials bi's defining the basis. Then A includes the polynomials ai, j, k that I told you about before, and S is the polynomials sij given as lists. And the rest of the proofs are, for example, these proofs of the polynomial identities that we can just solve automatically with decidability, or some of them with reflexivity. So if we are able to construct something of this type subalgebra builder, then we can obtain the corresponding subring O, which as a set is a Z span of the basis, but now with type Z subalgebra of K, which is what we wanted. And since we now have O and we have a basis for O, we can represent every element in O just as an n-tuple with integer coefficients. So in Lean, this would be something of type fin n to Z. And the way to do it is we just look at the coordinates of an element with respect to the basis that we have. And if we want to compute in O, well, we see that multiplication is completely determined by the pairwise multiplication of the elements in a basis. So we can collect this information in a multiplication table. The ij entry is just going to be the vector representing the product omega I times omega j. And from something of type subalgebra builder, we actually have all the information to construct something of type times table, which is this multiplication table. So times table is the structure that bundles together a basis of a ring, a multiplication table for this ring, and a proof of correctness of this table. And we can use then the vector representation together with this multiplication table to compute inside O. So we can translate arithmetic in O to arithmetic in these vectors. And we know how to deal with them because we have a multiplication table. So now that I told you how we can define O and how we can compute in it, let me say how we can prove that something is a ring of integers of K. So again, K is a number field of degree n, and we have a subring with a Z basis of size n. So it can be proven that a ring with these characteristics must live inside the ring of integers. And the way we can compare the ring of integers and O is by looking at the index of O in OK. So this would be the cardinality of the quotient OK modulo O. And we say that for a prime P, we say that if P does not divide the index of O in OK, then O is P maximal. So you see, if O is P maximal for every prime P, then this means that the index must be equal to 1. And this means that O must be equal to OK. So the strategy that we use is we're going to prove that O, the explicitly given ring that we have, is P maximal at every prime P. And in this way, we obtain a proof that O is equal to OK. And in order to do this, we use a theorem called the Post-Sassenhaus theorem, which gives us a criterion for P maximality. What this theorem says, in order to tell you what this theorem says, let me just briefly say a couple of definitions. So if we have an ideal I, the multiplier ring of I is just those elements in K such that when multiplied with I, we remain inside I. And here you can see the formalized definition that we wrote in Lean, and this is in a more general context. So we are actually talking about R algebras here, where R is allowed to be a principal ideal domain. But in our case, the one that I'm talking about here, R is just equal to Z. And now the P radical is going to be the elements in O, the elements X in O, such that there is a power of X that lies inside the ideal generated by P. And this is going to be an ideal inside of O. And again, here is a general description for this more general setting, where now pi corresponds to P. And what the theorem says is that if O is equal to the multiplier ring of the p radical, then O is p maximal. So we get a computational criterion for p maximality. And we can restate this theorem as a lemma in linear algebra. So actually we can define this map phi from O modulo PO to the endomorphisms of the p radical modulo p times the p radical, and we can prove that if the kernel of this map, which is an FP linear map, is trivial, then O is p maximal. So what we do is we define a certificate that proves the triviality of this kernel. And in this way, we are able to prove the p maximality of O. And verifying the certificate, so essentially the certificate consists of some number of elements that are mapped through this phi to some linearly independent set of endomorphisms. And to verify this certificate, it involves checking n identities in O and n identities in O modulo PO. But this is okay because we know how to multiply inside these rings. And the way we set things up makes it so that we can solve these goals automatically using, for example, decidability. And with Dedekind criterion, we can actually reduce the computation of proving p maximality for every prime p to just proving it for a finite list of primes. So what we did is we formalized some irreducibility certificates for polynomials because we needed those to convince Lin that K is a field. The maximality certificates that I described, together with the mathematics behind them, we wrote SageMath code that given an irreducible monic polynomial over the integers and an integral basis for the ring of integers, it gives you a Lin proof of O being equal to the ring of integers of K. And in this way, we were able to verify some entries of this big number theoretic database, which is the LMFDB database, for a choice of number fields, including 142 non-monogenic number fields of degree 5. And we also formalized some other computational tools, such as resultant and discriminants, which allowed us to, again, verify the discriminant of degree 3 number fields. And this is using that and using the fact that we can verify an integral basis. So this has been a case study in formal verification of number theoretic computations. Hopefully some steps towards bridging this gap between a traditional computer algebra system and a proof assistant. And the major part of the effort was not only dealing with formalizing the abstract mathematical content, but also finding suitable representations for computation. In total, we wrote 13,000 lines of code, and 32,000 lines of Lean code were automatically generated from our script to verify these entries. And some further directions for future work are perhaps optimizing these computations to deal with higher degrees. So in particular, the discriminant computations, which we were only able to do for degree 3. A tighter integration between SageMath and Lean. So right now, you press a button, you give the irreducible polynomial, you give a basis, and you press a button, and you obtain a Lean proof of the equality, which you can then import into Lean and check. But perhaps exploring a tighter integration would be interesting. And certifying other invariants that are also relevant for applications such as class group and unit groups. And yeah, thank you very much.
Thank you, Alain. We have time for questions.
Thanks a lot for this talk. So if I understand correctly, you in your computation, you're only dealing with polynomials where the degree is smaller than 8. So I would like to understand what is limiting you. Is it the computation? Where is the performance bottleneck, basically?
Right. Yeah, so in these identities that we need to verify, there is these particular ones that involve some exponentiation. So something needs to be raised to the p to the t power. this is all happening modulo p, so in principle this is fine, but still we're having some troubles with these computations for a big degree and a big prime, and we get timeout errors. And another bottleneck is in the computation of the discriminant of a number field. This requires computing determinants. And the way determinants are implemented in MATLAB, well, these are not very suitable for computation. And we haven't really tried yet to optimize these computations, but this should be doable.
Give the talk. I was wondering, can you give us some numbers on the efficiency of the different parts? So how much computation is spent in the computer algebra system, and how much time is spent for generating the Lean code, the Lean scripts, and how much time for checking within Lean?
Yeah. So generating the certificate using the computer algebra system and generating the code for these examples takes a couple of seconds at most. And this is because the discriminants of these polynomials are not too big. But this can be problematic if the discriminant is too big because it involves factoring some big integer. But right now, for these examples, only takes a couple of seconds. And then checking the proof in Lean, which is in two parts. So first, the proof of irreducibility of the polynomial, and then the actual proof of the ring of integers, takes in total for degree 5, which is the one that we did the most, around 30 seconds.
I guess usually an important part optimization of ideal computations is to use Grosvenor bases. Do you use them at all? Do you compute your own in Lean? Do you rely on Sage to provide the basis for you?
For this particular project, we don't need Grosvenor bases. So yeah, Grosvenor bases will come into play when we're dealing with ideals in the ring of polynomials. But right now, everything has a Z basis, so we can do everything with linear algebra.
Okay, thanks, Alain, for the talk. And congratulations for this distinguished paper award.